Hi guys, welcome back. And today I'd like to um, carry on a little bit with uh, with some ideas on quantum mechanics. Uh, and as I said, I will not follow a straight path to 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 get to where I want. I will just give you few ideas that at some point should make a puzzle that we can together we can put together um, as one basically. Okay, so what I want to talk about today is a couple of things. One is the role of psi. Psi is the wave function, and what it represents, and how to use it basically in very simple examples. So and then I will talk about superposition, wave function and superposition. Okay, so remember that this is energy, so this is h bar I. Okay, so this is the where the wave function is. Okay, it sits there in the Schrödinger equation. Okay, is the thing that you want to find out given the energy of the system. At the moment, I'm not going to discuss about the structure of the Hamiltonian, so the energy of the system, but just to give you an idea, usually is, as in classical mechanics, is composed by two components, which are the kinetic energy and the potential energy. Okay, so usually this is, we never talked about energy. We always talked about F equal ma. I will possibly make a video that that allows us to look at the energy version of this equation, that basically then leads to the Lagrangian and Hamiltonian formulation. Those two arguments are huge. I'm not going to touch upon them. They're very interesting. Basically, it's a different way to look at the equation of motion from a broader perspective. Usually, they take in consideration 6 variables, space and velocity at the same time, and then you have to define an energy, which is the Lagrangian, and then you can build up the Lagrangian and Hamiltonian, which are function of the energy and position of momentum. Okay, so this is just to say that it's very, if you think about, just give you a quick idea why the energy fixes the motion of something. Okay, um, that might be just an idea, but it might help. Suppose you are on a tip of a mountain or a hill, let's say a hill, and you have a ball here. Okay, the ball with a mass and a velocity. Of course, if you think about it, the balls can only roll on the hill, on the touching the ground, so it will start to speed up and then reach the certain amount of velocity max at the bottom of the hill. Okay, so as you can imagine, this from first principle you can say that the max velocity will depend on the initial velocity, definitely, because if you launch the ball it will reach quicker velocity, but it's naturally clear that it will depend on the height of this hill, right? Because if you remember the free fall, um, the formula for the final velocity depends with the time, with the height, where the object falls. So the higher is the object, the higher will be the maximum velocity. And similarly is the same in a hill. So you have a height that will give you some contribution to the velocity. If you think about it, when the hill is completely flat, the velocity will stay the same. So there is no increment in velocity. But if you start to tilt the hill, you will increase the velocity. Okay. So this is just to say that there are two components. One is the velocity and the other is the height. The velocity helps the kinetic energy, which is a function of the velocity squared times the mass. This is the kinetic energy. And the potential energy, which is mgh, which is U. Basically the energy that is stored by being in an elevated position. Is the potential, exactly, the possibility to express the velocity by moving down the hill. Okay, these two things together forms sum them together, if I remember correctly, without any sign in between, will give the Hamiltonian. Okay, so in general, there will be other forces that you can add, but usually you're happy with these two forces. You have a kinetic part and a potential part. In general, in many examples in quantum mechanics, this is true. In other example, it's a little bit more abstract in the sense that, and in some examples that I will give explicitly, the energy is mostly a function that changes the state of your system without being expressed in terms of kinetic and potential energy. It's just a mathematic. I will give you an example, but what I'm saying is that we don't need to fixate on potential and kinetic energy to get an Hamiltonian, but we can. In most of the cases it's correct, but in other cases it's just an analogy that we have to keep in mind, and there are other tools that we will use. But anyway, so having said that, we fix an energy and we solve this equation and we find our psi. Psi is of x and t, okay, position and time. So at any point in the space and at any time you get a complex number, okay, z, which is psi in that particular point. Let's call it star and t star. These are two particular points, time and space, and this is called z. Okay, so what does this tell us? At the moment is not much, but if you want to ask the question, what's the probability? Okay, so that's the thing. So this psi answer the question. One, what is the probability to find m, the particle, in x, t? Okay, so this is a very natural question in classical mechanics, because usually if you throw a ball, the probability to find it in, suppose you throw a ball, this is the trajectory, and then you can define an area, you can define this area, and you say what's the probability that the ball will be there, and then you can compute it with just a ratio of the area that you're considering with the trajectory. You can narrow down the area in a very specific section, and then you can even shrink into a point. You can technically ask what's the probability of the ball to pass in that particular point in x and t, and usually in classical mechanics you can define your system in such a way that this probability is always 1 basically. So you can basically trace perfectly your trajectory, and this is because you can measure velocity and space at the same time. And basically this probability in classical mechanics is a bit a shady concept, because usually you have certainty of your trajectory. Of course, this is not true if you have some errors or some initial conditions which are different. So your trajectory can be actually a bunch of different trajectories, and there you can start to see why the probability makes sense, because you don't know where your starting point is, so you have an uncertainty to begin with, and therefore you have an uncertainty in the end, and it makes sense to think about probability because you don't know where your projectile or your stone will land exactly. But this is due to lack of knowledge of your system. Basically, you don't control perfectly your system, you don't have all the tools about the atmosphere, the pressure, humidity, the surface tension, whatever. I mean, there are many contributions that can lead to this uncertainty in classical mechanics. What I'm trying to convince you, at least what the theory says, is that in quantum mechanics, even if you have a perfect understanding, as perfect as you can, of your system, the equation of the motion will not give you something that is certain, but it will give you some distribution of probability of being in a place. Meaning that in the best situation, anyway, you are driven and you are, let's say, bound to some uncertainties, as if your system cannot be specified accurately as much as you want. And by the way, this is very important because this is a conceptual step from classical mechanics to quantum mechanics, and we need to deal with it basically. In the perfect situation, you will get only probabilities for your answer. But how to get to these probabilities? So it's quite easy. So you basically you do this, you integrate over suppose you want to know the position in around a small volume, and then you integrate the modulus square of your wave function at time t around this volume. X is varying in the x, and this is the modulus square. Okay, this is okay. There is no, okay, I cannot give you a simple understanding of why this is true. I will maybe in future videos give you an idea how some very clever physicists come up with this formula basically, with this idea. But what I want to stress is the fact that your wave function is a complex number that is not directly easy to access. There are ways to measure it indirectly, but what you definitely can do when you solve this equation, you can find the probability of your system of being in some position or in some space with a volume v at time t star, for example. Okay. Okay, this is already quite nice. This is this integral here. When you deal with discrete vectors, not space but other variable, or you discretize your space in tiny chunks, and then you deal with vectors rather than functions, you can write it as a scalar product. So we know two vectors, you can get a scalar product and you do the square of it. The scalar product of two vectors, we know what it is the sum of the component of the two vectors between 1 and n. where A is a vector of A1, A2, AN, and B is the same. So, okay, so this is just to tell you that if you have your wave function psi, and then you think about it as divided into many bits, because maybe your space is discretized, your measurement system is discretized, or your resolution of your experiment is discretized anyway, or the system itself has just a countable many number of variables. There are examples of that, and I will give them. For example, if you think about, I mean, I will give an example of this, but okay, let's be easy. So this discretization can happen for many reasons, and then that integral that I told you is basically the same as doing the scalar product of your vector. Okay, and the scalar product is telling you the length of your vector. The scalar product of your vector in the region that you're considering. So V, which is the subset of position that you consider. So suppose your vector is spread around all the space. This is all the space, and your volume is only this bit here, volume here, and then you take your whole vector times your scalar product with just this bit of space that you are considering, and then you find the probability will be there with certain numbers. Okay, so nice. So as you can see, this is already interesting, because you start with some vector in a complex plane, and then you end up with a real number with a probability, and which you can measure and you can see in the lab, and you can do your experiment with. Okay, but there is a jump between complex and real numbers. Okay, and I think you agree that we might be missing something in this jump. In fact, if you think about a complex number z, usually it's modulus of z e to the I phi. It's expressed by two real numbers, okay? The modulus, the length, and the phase. We know that complex number can be thought as a vector with an angle. The length of the vector is the modulus, and the angle is the position with respect to the plane. This is real number, and these are imaginary real numbers, so I times r. Okay, nothing new, we know that. But when we go from this to the modulus square, we get rid of the phase, because the modulus square somehow, okay, if we modulus square clearly get rid of the phase, but even if we multiply two complex numbers and then we do the modulus square, as we can see, when we multiply two complex numbers and we do the modulus square, the phase plays a role, because we have z1 times z2 e to the I phi 1 minus phi 2. Okay, and then you take the modulus square. But this phase can play a role, because it can add some structure, some real value to this number. Okay, so this is tricky, because as you can see, when you multiply two complex numbers together, the relative phase of the two complex number can play a role. Fine. This relative phase can then be seen in the probability, because if you think about what I said before, when you have a vector psi along the space, and then you only see one section of it, you are basically multiplying two complex numbers. the full wave function against just the bit that you're interested with. And these two bits will have different phases, possibly, and the relative phase between the two will play a role could play a role in the probability. So it's subtle because basically it means that in quantum mechanics, these weird amplitude, which are complex numbers, can show this oscillatory behavior or phase dependence, if you like, that is not directly observable, but if you measure the probability, you can see it happening, depending on the situation of the experiment and the measurement device that you're using. Okay, so what I want just to say to conclude this short video is where this is one is the phase, the probability jump with the wave function that I said. I just touched a bit about measurement because I said that you basically do the scalar product of your system with a subset of what you need, which is expressed by your measurement. I can be more precise on this, but at the moment we just need to know that a measurement basically select a part of your wave function, okay? Projecting some subset of your wave function and take the modulus square. But one crucial thing about quantum mechanics is the superposition. So as you can see, we're talking about vectors, okay? And then you can have a wave function, and then suppose you have another wave function and you add it to it. You can do that because if both of these wave functions solve the Schrödinger equation, even the sum will do. This is easily seen because the derivative is something that we saw that the derivative of the sum is the sum of the derivative, and the Hamiltonian is a linear operator most of the cases, and then you can divide it. So what I'm saying is that if both of the wave functions solve the equation, even the sum of the two will solve the equation of motion, which means that if you have two solutions, even the sum of the two solutions will be a solution as well, so it can exist. But if you think about it, this is quite weird because the sum of two solutions, in some sense, implies that you have two possibilities happening at the same time, if you think about it, because you have one configuration of your system and another configuration of your system, some setting of the parameter of your system, the energy, the velocity, anything. It could be some particular characteristic, and both of the two are happening simultaneously, if you like, because the sum of the two systems will have those properties. And here you can see that, and in the next video I will talk about a bit of this, well, what happens when you have superposition that leads to interference pattern, okay, and oscillation behavior between two values. But what I want to say is that already in this case, it means that this state, we call it phi, suppose, will have a particular answer if you look at the system 1 and 2, the characteristic 1 and 2, because you can think about having the answer, what's the probability to get the answer 1 and then it could be 30%. And the probability of getting the answer 2 would be 0.7. But that means that for any combination 0.5, 0.5, 0.2, 0.8. And this is saying that your system is in an undecided state. It can jump between two values with certain probability. And this is not due to some configuration, some errors in your measurement device, or it's not due to the fact that you don't know your system enough. The best configuration that you can achieve, it's not determined, it's undetermined. And this is called superposition principle, meaning that you can have and you can have many of these one. Okay, you can have a huge superposition of many values, and in general this will lead to certain interesting pattern that you can exploit to do some clever or interesting feature, or it's just, if you don't exploit it, it's just the way in which nature behaves, so some effect will show interference pattern. I will close by saying that interference is not something that happens only in quantum mechanics. Any wave, even in classical mechanics, will have interference, something similar to the fact that there is the phase of these two complex numbers that is beating with each other. They are different phases, so they will oscillate with each other. But the difference here is that the reality of the system is a complex number, not a real number. So basically, we are saying that our interference happens to, in some sense, to the state of your system itself in a fundamental level. Okay, so this is a bit fuzzy, I understand that, but I'll try to be more clear with the example when I talk about the two-slit experiment in the next slits experiment in the next video, where I will show what happens when you have two wave functions that are competing with interfering with each other, basically in a superposition. And I will talk about the duality between wave and particle, which is closely related to the fact that we are dealing with complex number, but we jump to real number when we deal with the measurement. I hope this caught your interest. So today we discussed about the wave function, the square of the wave function to get the probability again, and then we touched upon the superposition principle, meaning saying that basically we have two possible realities that are happening, if you like, at the same time, and you're undecided which of the two outcomes will be with some probabilities. Okay, I will leave you with this, and see you next time.